Assalamu alaikum. So today we are going to talk about electrochemistry. Electrochemistry is all about what happens when electrons are transferred and how do we use electricity in that. Obviously, this is a topic that is usually taught in grade 11, but the syllabus advises that it is taught with redox reactions. So I'm going to do that. If there's any problem in there, then obviously we can always resolve that. But I don't think there should be. What do you need to do, or what do you need to know before you start this chapter is reactivity series, and you need to know what redox reactions are. We have already talked about what redox reactions are, but one definition that is super important for this one is that redox reactions involve exchange of electrons. So if there's an electron being accepted or something is gaining electrons, then we call that thing is reduction. And if something is losing electrons, then we say that thing is oxidation. So that is one important definition that you need to know. Second thing that you need to know is a few terms. Like the first term I would like to introduce to you is ionization. Ionization is when a neutral thing, like a molecule or an atom, so an atom or a molecule, it becomes ion, right? So it's not neutral anymore. Now that could be because it has gained electron or it has lost electron, but there's always a redox process involved and it becomes ion. The other one is discharge, and discharge is the opposite of ionization. So you take ion and you convert it to a neutral particle. So it could be an atom or it could be a molecule. And what happens is that you are getting, again, a redox reaction, but this time ion is becoming neutral. Let me give you an example. I take calcium, and calcium is a neutral atom. I convert it to calcium ion. Now, how will I need to do that? I will take the calcium atom and separate 2 electrons from it. So initially I had 1 calcium atom, but now I have a calcium ion and 2 electrons separate. So how do we read this statement? We say, we start with calcium. So I had calcium, which becomes, so this arrow means it becomes calcium ion and 2 electrons. So that calcium atom is now calcium ion and 2 electrons. Now this is a process in which we are getting an atom and it's becoming ion. So this is ionization. Now the opposite of this, if I were to put an arrow in the opposite direction and I read from right to left, what will it mean? 2 electrons and calcium ion. So I have them separately. So and means that they're separate from each other. Become, so this arrow means it become calcium atom. So this is discharge. So on the right side, you have ionization, and on the left side, you have discharge. But if you'll notice, both of them are redox processes. In the ionization, calcium is losing electron, which means it is oxidized. So in this case, ionization is oxidation. And the discharge is that calcium ion is becoming calcium atom, so that is discharge. And you can see that is reduction because calcium has gained electrons. If you take the a non-metal, so for example, chlorine molecule. So I take the chlorine molecule and I give it 2 electrons. So chlorine molecule and 2 electrons become chloride ion with a negative charge, and the 2 is there to balance. So I take 1 chlorine molecule, so they're chlorine joined together, and now each of the chlorine is separate from itself and they have a negative charge on it. Obviously, they have 7 electrons of their own and 1 electron that they have gained from something. Okay, and over here they're sharing 1 electron, chlorine, and that's the case. All right. So how this thing is different from the previous one is that this is still ionization. So the forward reaction is still ionization, but this is reduction because chlorine has gained electrons. In the case of calcium, it was oxidation because it lost electrons. The opposite, if I were to read this, it will be 2 chloride ions become 2 electrons and chlorine molecule. So what has happened is that I have discharged it. So the reverse process is still discharge. And what has happened is that you are losing electrons. So this is oxidation for chloride. Now, obviously, it depends on what you're looking at. If you're looking at something becoming a positive ion, that means it has lost electrons. So that is oxidation. Or if something is becoming a negative ion, so it has lost electrons. Sometimes you still have ions, but there's still redox reaction. So for example, if I have iron 2 ion, and it becomes iron 3 ion and loses an electron. This is still ionization. And this is still oxidation. Why? Because iron 2 has a positive 2 charge and iron 3 has a positive 3 charge. So that means iron 3 has lost 3 electrons, more electrons than iron 2 has. So that is ionization for iron 2, further ionization. And in any case, this is oxidation. So it doesn't have to be a neutral atom every single time. It can be some charged particle becoming further charged or a better or a higher charge, and that's oxidation, and a lower charge, which means it becomes more negative, that is reduction. So while I cannot call this thing ionization because I start with an ion, I can still call it oxidation. So redox is still applying here. Now, here's the principle. More reactive things means that they react, things or species, whatever. Now, if you're talking about metals, so more reactive metal is easier to ionize and difficult to discharge. Okay, and that is the case for whether it is a metal or a non-metal. So how is a metal different from non-metal? So more reactive species is easier to ionize, difficult to discharge. So for example, if I have a metal, then a more reactive metal is easier to make a cation. It's easy, a reactive metal, a highly reactive metal, but the reverse process is hard. But for non-metals, a more reactive metal, a non-metal, is easier to make an ion, an anion. That's easy, which means it requires less energy, but it is hard to convert it back to non-metal because that is difficult. Okay, it requires more energy. So that is the idea here. More reactive things or species are easier to ionize, difficult to discharge. It doesn't matter what ion you're going to make it. If it is more reactive, it will do it faster than the other. So for example, if you remember reactivity series, then potassium, sodium, calcium, magnesium. Let's just take this part. So I can see that if I were to convert potassium to potassium ion, I will need less energy. For sodium, I will take more energy. For calcium, it will take even more energy. For magnesium, it will take even more energy. Okay, so it's going to be easier, more difficult, more difficult, more difficult. And the reverse process is going to be magnesium converting back to magnesium atom is easier. Calcium converting back to calcium atom is slightly difficult. Sodium ion becoming sodium is even more difficult, and potassium ion converting to potassium is even more difficult. So the more reactive anything is, the harder it is to discharge. And the more reactive anything is, the easier it is to ionize. So that is something that you have to consider. Whenever you have something becoming ion, a reactive thing will become ion faster. And why is that? It has to deal with stability. We have been talking about it. A more stable ion is obviously preferable to an atom. So something becomes an atom, and if it has a choice between becoming an atom and becoming an ion, then it will always prefer to become ion because ions are more stable. Sure, they have complete shells, but they also have charges. So that charge makes them bond and all that, but still they have complete shells. So they prefer doing that. And this is the idea of electrochemistry. Now, there are two ways we use it. One is we use this when we want to convert ions, where we need ions. So for example, if I need, for example, I have a light bulb and I need it to, it has neon in it, or a tube light that has a neon in it. Now I want neon to become ion. So I will supply it electricity. So it becomes ion and it starts to glow. So that is one process where I need something to become ion. But let's suppose I already have, so my car, suddenly I didn't use it for a long time. There was raining and all that. And now my car is rusted. I don't want a rusted car, right? So I want that it goes back to becoming what it was. Rust is when iron ionizes and reacts with oxygen. I don't want that. I want iron to go back to becoming iron atom instead of iron ion. So that is, I want it to be discharged. So that is something that I will probably use some carbon that I will rub on it or something like that, so that it goes back to becoming iron. And because iron is a less reactive thing, it is quite easy to do that. So similarly, for example, if you are somebody in Jamaica and you figure out that, oh, wait a minute, we have these red rocks, and if I were to do something to these red rocks, then I could easily get aluminium from them, and that will make us a lot of money. In fact, the country's economy will depend on it. So you're like, okay, let's try to discharge all the ions of aluminium that are in this red rock. That red rock is called bauxite, and Jamaica has a really large reserve of it. So they would like to convert it back. But the problem is aluminum is very reactive. So it's quite difficult to discharge aluminium ion. So we need electricity for that. So electricity is the power that allows us to ionize or discharge things whenever we need them. So for example, I need neon to glow. Then even though neon is a noble gas, I can still ionize it by giving it electricity. So electricity forces it to do something that it doesn't want to. Noble gas does not want to become iron, but electricity will force it to do that. So I can easily ionize it using electricity. Similarly, aluminium wants to become iron, but ionic aluminium is not that useful to me as pure aluminium atom. So we can use electricity to convert it to back to aluminium atom. So when you use that, when you use electricity to convert ions to atoms, discharge, we call it electrolysis. So electrolysis is a process in which you break stuff using electricity. So what happens here? We've talked about displacement reaction, right? We know that if I have this same thing, so I'm going to write the reactivity series here. So it is magnesium, aluminum, zinc, carbon, lead, iron. Sorry, iron and iron goes. So hydrogen, copper. So let's suppose I have copper and I find rock where copper is. So copper exists as copper oxide. I want pure copper. So what do I want? I want this copper ion to convert to copper metal and oxygen, right? I can't do it right away because copper will not just simply leave oxygen. Copper ion is preferable. So I add hydrogen to it. Why is that? Because hydrogen I can see is more reactive than copper. So it's easier to ionize hydrogen. So what happens is that this hydrogen comes in, displaces copper and makes water. So what have I done? I have extracted copper. So this pink solid, I will see this, and this black rock will simply convert to a pink solid, and I will get steam because I am heating it. Obviously, I'm heating it. Similarly, I have iron. So iron oxide. I add carbon to it. Why? Because I know that iron is over here and carbon is over here. Carbon is more reactive. So I react them, I give it heat again, and now carbon dioxide is made and iron goes out. So I balance this. Sorry. And there you go. I'm able to get iron. So it heats and I'm able to get that. So iron atom is quite useful to me. Iron oxide, this thing, this is rust. It's not that useful. But if I want to get aluminium, then it's going to be a quite a difficult thing, because let's suppose I get aluminium as aluminium oxide in the rock. Then that aluminium, if I want to displace it, I will need to use either a potassium atom or a sodium atom or a calcium atom or a magnesium atom, and all of them are quite expensive to get themselves. So this is something that I don't want to do. I don't want to replace aluminium with something. I just want aluminium back. So what do? I supply a lot of electricity to it, and that electricity converts this aluminium ion to aluminium, it discharges it, and oxide ion to oxygen, and it discharges that. So this way, I'm able to get aluminium and oxygen separated from this using electricity. So where heat doesn't help us in redox, and where you need a reducing agent or an oxidizing agent, you can do without it by using electricity. So that is the main process of electrolysis, that what you do is you take anything that has ionic bond in it, and you obviously, if something has ionic bond in it, then it has ions in it, right? So you take that thing, you supply electricity to it, and it breaks it up. So you have an ionic compound. So ionic compound, you give it electricity. So there's electricity given to it. And now it's separated to a positive thing and or a non-metal. So metal or a non-metal or whatever it was made of. So and compound, so let's call it C, breaks down and forms A and B, which are two different things using electricity. That is called electrolysis. So how do we do this? For electrolysis, what we need is, we need, first of all, an ionic compound. No, what you call covalent compound will do it, because you need a pure. Sure, you can have impure covalent compounds that can do this, and we talked about them like acids or water that can do it. But what you need is ions. Okay, you need ions for electrolysis to occur because you're separating them. Okay, what do? So here's the setup. The basic setup is, you take a tank. In that tank, you're going to put the thing that you want to break up. So that is electrolyte. Okay, so you take an electrolyte. What is electrolyte? It is a liquid or a gas that conducts electricity. Okay, what am I going to do next? I'm going to take a battery, because battery will give me the electricity. And I'm going to put a bulb there just so I know that current is flowing. And I'm going to dip that in there and dip one side in there. Now, obviously, wires can be really small. So instead of having a small wire, I put a rod. This rod has a large area. So any ion that is attracted to it comes here. Now, here's the thing. Battery has a negative side. The smaller side is negative. So this becomes a negative side. This whole thing is negative. Similarly, this is a positive side. So this whole thing is positive. Okay. Now, what is my electrolyte? My electrolyte has a cation. So there's a positive ion, and there's an anion, which is a negative ion. Because remember, these are ionic compounds. What happens? As soon as I turn the current on, all the positive ions are attracted to this side and all the negative ions are attracted to this side. And they all just come in here and they are attached to this. And all the positive come here and they're attached to this. Now what happens? These positives are going to come to the negative thing. And what happens? If you take a positive thing and you add a negative thing to it, it becomes zero, right? It becomes neutral. So if something had a positive 2 charge, I'll give it 2 electrons because I have plenty of electrons. This is negative. So it will become zero, neutral. So I have discharged it. It becomes atom or a molecule. Similarly, the negative thing comes to that positive side and it obviously loses electrons because negative means it already has a lot of electrons. So it loses them and now it is neutral, right? So on both sides, I'm going to get neutral things. Now, the positive ion is cation. So that cation comes here. So I'm going to call this cation's electric rod. Now that's quite a mouthful, cation's electric rod. So I don't like that term. I'm going to call this, instead of calling it cation's electric rod, I will call it cathode. That it is where cation will come. This is the electric rod where the cation will come. Similarly, this one is anion's electric rod, but again, that's too long. So I'll call it anode. That this is where the negative thing will come. What exactly am I doing? I'm breaking down an ionic compound and I'm separating pure substances from that. If you remember, in filtration, we talked about, for example, the idea of separating salt from sand, and we added water, and then we put a filter there, and sand was separated and salt was separated, right? That's a physical process of separating things. Electrolysis here is a chemical process of separating things. I'm breaking stuff up. So let's take an example and see what will happen. So I have sodium chloride. So that is what I have, sodium chloride. But what do I want my rods to be made of? My rods can be anything that conducts electricity. So I can have graphite or I can have a metal. I will prefer graphite because graphite is inert. Okay, so these rods, which I call electrodes, basically electric rods, electrode can be inert, which means it doesn't react, or it can be reactive, which means it does react. So inert electrodes are carbon or platinum. They don't react. They're very less reactive. Sure, carbon does react at high temperature. So carbon reacts at high temperature. On the reactive side, I can have any other metal like copper or magnesium or calcium or iron or anything that I want. And that will help me later on. It can be gold even. Okay, so I have sodium chloride. That's my electrolyte. So that's my electrolyte, sodium chloride. What happens? So what ions do I have? So that's the first thing I need to know. What ions do I have? So sodium is sodium ion and chloride is chloride ion, but there's a problem. Sodium chloride is a solid and solids do not conduct electricity. So I need to melt it. So I melt it. So that means I need to supply a lot of energy for this. So I will supply a lot of heat. This thing melts. Now I have sodium ions separated, chloride ions separated. So I have sodium ions, I have chloride ions. All right, so what happens now? At the anode, my chloride goes. So chloride is going to be attracted to the anode. It's going to become chlorine molecule, right? Obviously, how does it do that? It loses this extra negative charge that it has. Where does it get the electric charge from? It gets the charge because it has extra negative ions, extra negative electrons. So it loses those electrons, become chlorine molecule, neutral. Good. What color is chlorine? It is yellow-green. So I will see yellow-green fumes. So chloride comes, loses the charge, becomes chlorine molecule, and flies away. Obviously, I can collect it if I want. What happens at the cathode? So I have sodium ion that is going to go to the cathode. It's being attracted. It's going to get electrons and become sodium atom. Sodium is a yellow solid. So I will see yellow liquid. Why? Because the temperature is quite high. But you don't need to know liquid hoga, solid hoga. You don't need to know that. Now here's the thing. If you notice, I gave 2 electrons to this anode. So those electrons were deposited here by the chloride. So those electrons must travel over here. But sodium is only needing 1 electron. But I need to balance it out. So I give sodium 2 electrons. And sodium is like, wait a minute, I don't need 2 electrons. But I have a friend of mine who does. So sodium brings another sodium. And they both react to make 2 sodium atoms. Why did we use 2 electrons in the beginning? Yeah, that's a good question. We needed 2 electrons because 1 chloride has 1 extra electron, but we need 2 chlorine to make a molecule. So that is why we need 2 chlorides that will both give 1 electron each. So they lose 2 electrons and you get chlorine molecule. Remember, chlorine is a diatomic gas. So what happens here is that you will eventually see that all the sodium chloride has been separated into green gas, which is chlorine, and you can collect it. You can use it for whatever you want. And sodium metal, which also you can collect for many different reactions, like making sodium hydroxide or stuff. And there you go. You have separated sodium from chlorine. And this is remarkable. Why? Because this was something that people for the last 2000 years ago had absolutely no idea how to do it. It was only after we harnessed the power of electricity and started using it that we figured out that, oh, we can actually separate stuff, chemical stuff, using this. I'll tell you a reason. I think 200 years ago, aluminium was more expensive than gold. And do you know the reason? The reason was that aluminium is a very reactive metal. So if you found it, you never found it in pure form, because if it was left outside, it would react with oxygen. If it was left in some rock, it would react with that, whatever was in the rock and all that. You never found aluminium in pure form. So, but in case you did, people prized it. It was so expensive that the King of France, Napoleon Bonaparte, if, for example, you were invited to his palace, then if you were a normal guest, they would give you cutlery and knife and plates and cups made of gold because you're a normal guest at the King of France's banquet hall. But if you were somebody who was quite like some prized guest, some really important guest, then they would serve you in cutlery and cups and these things, plates made of aluminium. It was that expensive. It was considered to be the most expensive thing ever because it was shiny, more than gold, and it was very rare. But fast forward to today, and we actually wrap aluminum in, we actually use aluminum to wrap sandwiches that we give to students when they're going for lunch or on a trip. We make our window panes using aluminum. We use aluminum to make aircraft planes and all that. And why is that? Did we find a great reserve of aluminum? Sure, we did. But actually, we realized that aluminum reacted with stuff, and that's no problem for us. We have electricity. We can get aluminum back. So that's it. You don't need to value aluminum as much. But gold is still valuable because gold was always unreactive and all that. So it turns out aluminum is the most abundant metal on Earth. 8% of Earth's crust is aluminum. And we were so worried that, oh, this is a rare thing and all that, just because we did not understand electrolysis. So you can separate stuff that is very difficult to separate, that has really strong bonding, just by using electricity. Let's try another one. So we have another electrolyte, and this time I have, electrolyte. So this time I have Al2O3. What is that? That I get from, this I get from bauxite. Bauxite. That is the ore of aluminum. Do you understand what ore is? You might have heard about it in geography. Do you know what an ore is? So ore is something, it's a rock or the natural reserve in which you get any metal. That's what ore is, okay? So for aluminum, that ore is bauxite. That's the major ore. Sure, there's another one, cryolite. Now here's the thing. We want this to be the liquid that we're going to separate. So this is aluminum oxide. The problem is aluminum is very reactive. So there's a lot of energy that you need to break this lattice. So what do? We give it a lot of heat, but turns out it melts at almost 2000 degrees Celsius. So if you try to do that, your electricity bill for melting it will skyrocket. So you don't want that. What do? You add cryolite as an impurity. And remember, what do impurities do? They lower the melting point. So that's exactly what cryolite is going to do. Cryolite is going to lower the melting point of this thing. And now we have aluminum oxide in molten form. So you have aluminum ions, you have oxide ions. They're both floating around, swimming around in this electrolyte. So you dip the two electrodes that you have, you connect them to a battery because you want an source of electricity, a bulb to know whether current is flowing or not. And there you go. Now you're ready. So this side is positive and this side is negative. So what's going to happen? The oxide is going to go here and aluminum is going to go here. So what happens? What ions do you have? You have aluminum ion and you have oxide ion. All right. So what happens at the anode? So at the anode, this oxide is going to come, drop the 2 electrons that it has and become oxygen atom. But does oxygen exist as atom? It does not. Oxygen actually exists as molecules O2. So you need 2 oxygen, which means every one of them is going to lose 2 electrons. So 2 will lose 4 electrons. So you're just balancing this thing. So you get 4 electrons dropped at over here. Those electrons are going to transfer from here to here. And what happens there? At the cathode, you're going to get aluminum ion. It's going to get 3 electrons. It's going to form aluminum metal. And voila, you have gotten aluminum metal, something that even Napoleon Bonaparte would be quite envious of. But here's the thing. You gave 4 electrons, but you received 3 electrons. So you have to balance this out. What is the LCM of 4 and 3? Tell me. Jaldi bataye. What is the LCM of 4 and 3? It is 12. Yes. So we have to make it 12. So how do I multiply? What do I multiply the first equation with so that I get 12? 4 times what is 12? 3. Yes. So what I'm going to do is I'm multiplying the whole thing with 3. So 6O2 minus 12 electrons plus 3 oxygen. And this one I'm going to multiply with 4 because I need it to be 12. So 4Al3 plus 12 electrons makes 4 aluminum. And there you go. We are going to use aluminum oxide and we're going to get this much aluminum. How much aluminum and oxygen will you get? The ratio will be 3 to 4 and the electrons are balanced. So you will get oxygen coming out and aluminum on the other side, which is silvery metal. and you're good to go. One problem, you notice that because you used this rod that was made of carbon, suddenly the carbon is gone. And that's quite worrying. Where's the carbon gone? Turns out, because of the high temperature, carbon reacts with this oxygen that you produce and makes carbon dioxide. And now the anode, which was made of carbon, this one, is gone. After a while, you see that carbon just converted to carbon dioxide, it evaporated away. And now you get another one. So anode has to be replaced. But that's fine. Carbon is really, really cheap. Sure, carbon dioxide is dangerous for the environment, like higher amount of it. So, but anode has to be replaced. So we keep on doing this. We keep on getting aluminum. We keep on making aeroplanes. We keep on making window vanes. We keep on wrapping our sandwiches. And so it's all because we have the power of electrolysis. All right, a few ionic compounds that I need you to figure out the electrolysis of. So there's the lead oxide, lead iron chloride. And I want you to figure out, would it be possible if I gave you a rusted car, can you still get pure iron out? So these three, try to figure out if you can do it. All right, and tomorrow we'll talk about more practical problems associated with electrolysis.